kind of flow that we analyzed was the barotropic flow, okay, where we have almost all the terms with the exception of the variation in the vertical, so we have no shear, but we still have Rossby and the two Rossby numbers which are ordered than 1, okay, but we don't have any kind of friction. And finally, we analyzed the Ekman layer, which allow for the presence of a solid boundary and therefore or a friction. Okay, so all of these were actually very simple also from the mathematical point of view, because as you have seen, we didn't have any kind of very difficult differential equation to be solved. So there were very simple cases to be analyzed analytically. Same thing we can say with the last part, which is related to waves. So why waves? Because as said on Friday, what we have here is that we can we can consider this solution when we linearize our equation. So when we linearize the equation, we put some restriction in the equations, and putting some restriction, we hope to have an easy solution to be considered. In particular, we analyzed each of the terms of our system, and since our hope is to linearize, so linearize means that all the things that have dependence of second order with respect to the velocity or any kind of other unknown, but in our case it's only the velocity, can be neglected. This means that both the velocity, but also, for example, if we should have non-homogeneous fluid, we have something like terms like this, okay, which are in any case nonlinear. Okay, so since we are now again considering a homogeneous fluid, so we do not have any worry about that, but still we can consider a simplification of any terms that has this multiplication between the velocity, and which actually are order of u squared over L. Okay, this means to linearize the equation and therefore to have another kind of simplification of our system. So in this case, that Coriolis terms are linear, so still Coriolis terms are the let's say leading term in our equation system. The other thing is that if we want to neglect the advection which are not linear, we may consider the Rossby number much smaller than 1. Okay? So Rossby number much smaller than 1 means that u over omega L is much smaller than 1. This means that u is much smaller than omega L. So the velocity of the flows is quite small if we compare it with the typical velocity related to the rotation frequency. But we can also consider, okay, if we fix this, we can also consider very large scale. Okay, so we have relatively weak flows, relatively large scales, and then we can also consider, if we are in a laboratory, we can increase, of course, this as much as we can, and keep this at the scale of the laboratory. Okay. So the other term that we still want to keep is the local time of velocity, which is like this, and have its case like this. So when we consider the ratio between this one and the Coriolis term, we have the temporal Rossby number, which is order of 1, okay, or smaller than 1. But for sure, it is not much smaller than 1, okay? So as we try to intuit think about last time, what we are considering as slow flows under rotation that evolve relatively fast. So we have some sort of disturbances that are rapidly moving and do not require large velocities, okay? So the typical example is when you throw a stone in a pond, and what you have is that if you consider the velocity of the parcel, of each parcel, is not so much, because it's, I mean, it can be like this or like this, it depends on the velocity, on the kind of disturbances, but the information spreads very fast from the center to the periphery of the area interested to the motion, okay? So the L, the capital L, in this case can be considered as the radius of the circuit that can travel very, very fast. Okay, so what we obtain is the system which is still, let's say, relative of the barotropic flow system, but what we have is that the first two terms, of course, contain only the time derivative, local time derivative, and the Coriolis term, and the pressure terms, while the continuity equation contains only this one. Okay, so let's have a look how we obtain this, because if you remember, we started. We leave here our hypothesis, so we have that. Okay, so one more scale, we will call it capital C, and this is actually the ratio, the velocity, which is related, it is different from u, because it is related to the horizontal scale, or the distance covered by the signal, which is actually, for example, like in the example of the stone in a pond, is the radius of the circle, okay, so of the wave. So this has, we can, it's like, okay, so 1 over t, sorry, 1 over t is order omega, and if we have omega multiplied by L, we know that this is much smaller, much larger than u. Okay? So the velocity of the signal is much larger of the velocity of the parcel. Okay? So this is the trick that this kind of flow is characterized. So our shallow water model was dt u minus fv equal to minus g dx. You remember that we have h here, no? So now we have a situation where, for example, we have the bottom, then we have capital Hxy, which is the bathymetry, and then we have also the variation of the surface. Okay, we can call it like surface height. Okay, so we can consider as a level, a reference level of our fluid. Again, can be air, of water. Of course, thinking about water is a little bit more easier. And then we have H, which can be considered or like the mean topographic field, okay, or if in case of flat bottom, this can also consider a constant. Okay, so it's doesn't change too much our consideration. So what we had in the last consideration of the barotropic flow, we have that the actual sum of eta and capital H was our H, which was present, if you remember, in the shallow water body. Okay? So actually, we neglect these four terms. We substitute here to capital H the sum of eta and capital, to low case h the sum of eta and capital H. And then we make some analysis. So we have this one, we have the second one, and then we have the continuity equation. Okay, when we have H here, the only dependency on T is on eta, plus, so we have H, so eta plus capital H u plus dy eta plus capital H v equal to 0. Okay? So consider this hypothesis, okay? So considering the flat bottom, and look what happened to this term here. So here we will have dx, so this can simply like this, and this can eta v plus capital HV. So when we want to make the derivatives of each term, of course, if h, capital H is constant, what we obtain is that we consider the first, then we gather the terms which apply the derivative to eta. So we will have u dx eta plus v dy eta. Then we gather the term related to capital H, dxu dy v. And finally, the terms which are related to eta. Okay, again, scale analysis. So we will give a new scale to eta, which is delta H, delta capital H. So this will be delta capital H over T. This will be U delta capital H over L, okay? This will be H U over L, and this will be delta capital H U over L. So we have 1 delta H over T, 1 H U over L, and 2 U delta H over L. So we can take the ratio again of this term here with respect to the first one. So what we obtain, so we have delta H goes to 0, and so we will have UL over T. But UL over T, since L over T is G, so we have UC, which is much smaller than 1. Okay? So these two terms actually, sorry, not this one, can be neglected. And so what we obtain is the final form of the equation of continuity, which only consider the local derivative of eta and this term, which actually is the multiplication of the mean depth, we can call it, and the horizontal divergence. Okay? So, and of course, over the two equations, if we consider h constant, we just remain with the variation of eta. So, this is just eta. And here we just have okay. So these are this system of differential equation is governing the linear wave dynamics. Okay, so if you don't remember about waves and so on, you can find in Appendix B of the Gushman a very short recap of all the wave dynamics, considering, for example, the wavelength, the wave number, the period, frequency, and all these things. Phase velocity, group velocity. Do you remember? Some of you yes, some of you no. Okay, so just take some half an hour or something to review this, because in this part is very, very important. Okay, so now we will try to analyze four different cases. Just four different cases of our system. Okay, so we have again three differential equations in three unknowns, u, v, and eta. We start from the yes, sorry, there is one more point. If we analyze, because we need to have something about delta h. So if we analyze these two terms, this will be delta h over t, and this will be h u over l. Okay? So these two terms actually, since are in the same equation, are in balance. Okay? But if we consider right here delta h over h, this will be u t over l, which is u over c, which is much smaller than 1. Okay? It's something that we, in some sense, we have, we could have hypothesized, which means that delta h, so the scale of eta, is much smaller of h. Well, it's pretty, I wouldn't say obvious, but something that we can expect. Because the oscillation, because we are talking about disturbance oscillation related to the barotropic waves, so the amplitude of this oscillation, which is measured amplitude in terms of height of the column, of the fluid column, is much smaller, of course, of the scale of the mean depth. So we are considering small waves over the surface of the ocean, okay? Or other waves which are, for example, on the atmosphere at the discontinuity between the troposphere and the part in the stratosphere. Of course, in that case, don't forget that we are also discontinuity related to difference in density, which here we are not considering. Okay? Good. Okay. So let's start with the first case. So that's why we call it like small amplitude waves. Okay? In a rotating, homogeneous, envisaged flow. So still no friction. We are far from the friction. We are far from the bottom. And so we don't are interested in the friction. Okay, the first case that we are going to analyze is called Kelvin wave. Okay, so Kelvin wave was hypothesized by Lord Kelvin, which is here, and he said, okay, if I have this system here, one thing that I can require is that I have a lateral boundary layer as support, where at x equal to 0, I have that my velocity is equal to 0. So what I have is that, like, so for example, this is the land. This is the ocean. This is the y coordinate, and this is the x coordinate. Okay? So at x equal to 0, which is along this axis, I have the two velocities as equal to 0. Moreover, the strongest and even strongest hypothesis, which is, I mean, this is could be reasonable, because we can say that we do not have any kind of slip at the boundary. But what Lord Kelvin added was to consider u equal to 0 in the whole domain. Okay, so from our system, what we obtain is a system which has a perfect geostrophic balance in the x momentum, and then two equations So actually our system is degraded to a system with still three differential equations, but just two unknowns, okay? So the two unknowns are v and eta, because u is a solution which is equal to 0. Okay, so if we consider these two equations, and we can see that there is just a variation in t and a variation in y. So if we make here, we apply a partial derivative on t, and here we apply a partial derivative on y, and we sum the two equations, what we will obtain is the differential equation of second order that we can see over there, which is a wave equation, okay? Where C is equal to the multiplication of G multiplied by capital H. And this is the velocity, the phase velocity of surface gravity waves. So from the analysis of the second and the third differential equation of our system, we were able to neglect and to cancel the dependency on eta, and we just obtain a wave equation which is related to a phase velocity equal to g multiplied by h squared, and this is a definition, is a new definition, something that we never seen. Which of course, and is completely, let's say, independent from the fact that we are in a rotating flow. Okay, so this, we don't have any kind of dependency on F, okay? Because the only dependency on F is in the X momentum equation. We are just considering something which is non-rotating. So actually, if this is a disturbance that travels on a non-rotating two-dimensional flow, this will have gh squared as velocity. And this velocity you can consider that is quite high, because if you take, for example, for, let's say, h equal to 1,000 meters, okay, like in the ocean. And g, of course, is 10 order 1 meter squared per second. So the multiplication of this is 10 to the fourth, okay? When we make the radius, we will obtain that c will have 100 meters per second. So this hypothesis here is strongly, significantly correct, because you remember that the velocity in ocean is about 0.1 meter per second. Okay, we can do something similar also for the atmosphere. Is more or less the same. We can also consider if you like, even 10 meters. Okay, so very small, very shallow depth, and we will obtain 100, and we will obtain 10 meters per second, which still is 1 order or even 2 order of magnitude larger than the typical velocity of the flows in the ocean. So this equation here has a typical solution, which will be the sum of two waves. So one, which is traveling in the opposite direction with respect to epsilon, and the other one, which is traveling in the same direction of epsilon. Okay? So this is, I mean, no GFD, this is like pure mathematics. Okay? So if we work a little bit with this, and we put this expression here in the y momentum equation, what we will obtain is a first approximate solution of eta, because we can include v1 plus v2 here, okay, because this is the most general solution, right? So we do not have any kind of boundary condition at the moment to apply. So in the most general case, v will be the sum of these two waves. If we put v1 plus v2 here, when we make the time derivative, we will obtain c, and we can then integrate over h, and what we will find, you will of course find all the details in the book, is h over g v1 plus h over g v2. So now, if we put these two terms in the first equation, in the x momentum equation, so we can separate the two equations, and what we will have will be, so minus f multiplied by v1 plus v2 minus g, and then I will have to make the x derivative to the expression of eta. What we will have is two equations, one for v1 and one for v2. So, of course, these two equations can be very easily solve it, and what we will obtain is an expression of which will have as a solution something which has a dependency, an exponential dependency, so in the most general case plus or minus, in the dimension x over a term r, where r, again, is a new object, and is defined as the Rossby radius of the formation. So the equation that we will obtain will be V1 equal V1 0 y plus Ct e to the minus of r, and V2 will be V2 0 y minus Ct e to the minus xr. So what this means? This means that V1 0 and V2 0 are sort of condition that we apply when we solve these two equations, and we will have that V1 and V2 have a dependence. Oh, sorry, this is plus. Yeah. Have a dependency that is exponentially decreasing or increasing with x. Okay, so the velocity, the two component of my solution V1 and V2, will have a dependency which is wave-like, multiplied by a decreasing or increasing dependency when we move offshore, okay, so far from the coast. And the distance, the scale of this dependency is r. So what is r actually? R can be also written as c over f, where c is our surface gravity waves velocity. And actually, this helps us that if we consider a circle with a radius r, so the velocity will be 2 pi over r divided by the period t. Okay? So if our period t is exactly 2 pi over f, which is the period of, do you remember? 2 pi over f is the period of the inertial oscillation, okay? Case 0 that we analyzed, just considering the system of rest for a non-rotating system, okay? So if we have this, we just obtain, so we just can r 2 pi over f. And so we will obtain again c over f. So what does it mean? It means that the Rossby radius of deformation is nothing more than the radius of a circle which is rotating with a period which is the one of the inertial oscillation. Okay? So, and if you remember, this is exactly the same function that we found when we analyzed the inertial oscillation over a two-dimensional plane. So, this scale here, r is the distance for which this term starts to be much smaller than the term at x equal to 0. Okay, when x is equal to 0, the two velocities are equal to v1 0 and v2 0. Okay, we are here. Then the velocity, the value of the velocity, will increase or will decrease. Of course, we can say that this solution here is not feasible because we cannot have velocity which increase without any kind of energy support. So we can neglect this one. And the term here tells us that when we will have x equal to r, or equal to 2r, or equal to 3r, or 10r, so increasing r, of course, this term will make a sort of exponential decreasing of the velocity. So we can say that when we are quite far from our const line, the velocity v goes to 0. Okay? That's why we call these waves trapped. Trapped because in a distance of r with respect to the cost, we will have that our velocity will tend to go to 0, will tend to disappear. Okay, so we can define a new function. So since this is a velocity, okay, so the measure, the unit measure of this one is velocity because it's the value of the velocity at x equal to 0. So we can represent u0 as a scale of the velocity c multiplied by a certain function f, capital F, which only depends on the y plus ct term. And what we obtain are this solution here, okay? So v will have multiply gh by f e to the minus xr, and eta, which actually is this one, okay, because we just remove the dependency in v2, and what we obtain is just to multiply this part here by capital H over g, and so we just obtain minus hf multiplied by the exponential decrease in x. So this is the solution of the Kelvin wave, and is pretty interesting because what we will have is that if we have eta positive, so when we have eta positive, of course v will be negative, and the opposite will be true. So the propagation of the wave is always y plus ct, okay? So it means that will be always on the contrary with respect to the y direction. Because we had before we had two possible waves, one in this direction, one in the other direction. The one in the other direction was removed because of the explosive increase far from the wall. So we have that our wave, the disturbance is traveling always in this direction. Okay? But actually, this doesn't mean that the velocity must be negative or positive strictly, because the velocity can be positive and negative, because this f here can be positive or negative. These two, of course, must be positive. And eta will be always the opposite with respect to our v. So if we will have eta which is positive, so it means something that will go like this, okay? So when eta is positive, v will be negative, so we'll travel in the same, the velocity will have the same direction as the wave. In the other case, if eta is negative, the velocity will be positive and parallel in the same direction of y. So it's a little bit difficult to visualize here. That's why Cushman provides our nice picture. So you can see here that the wave propagation is always directed opposite with respect to y. And in this case, we have eta, which is positive. In this case, we have eta, which is negative. So when eta is positive, we have upwelling. And with upwelling, we are traveling with in the same direction of the wave. When we have eta negative, we will have downwelling, and the velocity is in the other direction. So it's opposite to the wave propagation. Of course, we are still looking at the northern hemisphere, because otherwise, as in the previous cases, everything will be reverted. And in the northern hemisphere, both waves travel with the coast on their right. Okay? So what is exactly the meaning of this curving wave? Actually, we are still looking at something which is in geostrophic equilibrium, okay? Because this is still applying. And this is a disturbance which is added to the geostrophic equilibrium. Okay? So it's a wave which is traveling within the geostrophic flow. So geostrophic equilibrium x momentum leads to a velocity that is maximum at the bulge and directed as geostrophic equilibrium requires. So v will be always proportional to g over f d eta dx. Because of different geostrophic velocity at the bulge and further away, convergence and divergent pattern create a lifting or lowering of the surface. The lifting and lowering is such that the wave propagates toward negative epsilon, in either case positive or negative bulge. Okay? So it's a disturbance which is traveling, which is characterized by inertial frequencies. Okay? And can be used to describe a system like the one which characterizes the tidal flow in the channel between France and Great Britain. Actually, since in this case here, so we can consider these are the channel, UK here, France here. So the disturbance is in this case the tidal flow. So tidal flow is entering from west to east, which means that our y-axis is reverted. So we can put y-axis here and x-axis here. So since the wave, we are in the northern hemisphere, curving waves always travel with the coast on their right, it means that they will have, if they are moving with the coast on their right, it means that they will travel with this direction, okay? V will be negative with respect to y. So we are in this case here, and so we have upwelling on the France coast. Okay? This explains very roughly, but analytically, in a very analytical, let's say, nice and clean manner, why when we want to measure the height of the tide in the channel, we will always have that the highest tide are on the France coast rather than on the Great Britain. So here, these are the dashed line are the times. So after 5 hours, 6 hours, 7, 8, 9, 10, and so on. So this is the progression of the wave, and the solid line are actually the height. So it's a measure of eta. Okay. So here we have 6 meter, 5 meter, 6 meters also, and also here much more. And here we have 2 meters, okay? So we have 4 meter maximum of difference between the effect of the Kelvin wave of the France coast and let's say the decay of the Kelvin wave towards the UK coast, okay? Good.
I think I might be wrong, but first I think you wrote that x equals 0, both u and v were equal to 0, but v can't be 0.
Maybe there was a problem. Maybe it was only u equal to 0.
Because if not, v
no, yes, of course.
f will be 0 everywhere.
Absolutely. Yeah. We can, if you like, we can even consider a very small boundary layer where actually the velocity goes to 0, but after a while we can consider a v which is not equal to 0. Yes, totally correct. I think, by the way, there is also an error. Try to look on the PDF, because maybe also in the original, or maybe there was a sort of problem, misunderstanding in the slides. Okay, second kind of waves. So, POINCARE waves, given who had the name by the mathematician, the French mathematician POINCARE. I think it's POINCARE. I don't know. And it's correct. Not POINCARE. POINCARE, I think. So he said, okay, let's be a little bit less restricted than Kelvin and keep u not 0 in the whole domain. Okay, so let's allow that u is fully present in our system. So we do not have any kind of boundary, because Kelvin waves, to be sustained, must have a boundary. And actually, if you remember the picture of the geostrophy taken by the satellite, the Kelvin wave actually can travel in the northern hemisphere always with the coast on their right, and actually, as I said before, represent a sort of disturbance or perturbation of the geostrophic flow. Okay, so the picture that we saw before and the analysis that we made, like considering like a sort of blocked basin with no topography and so on, just by considering the height of the surface and the measurement of the height of the surface with this, from space, from the satellite, was actually explained with a little more precision by the Kelvin waves. Okay, so POINCARE said the system has to be solved entirely, and we can keep that all coefficients are constant, and we can found for a Fourier-like solution. Okay, so we hypothesize that the solution of our three unknowns, eta, u, and v, are proportional to capital A for eta, capital U for u, and capital V for v, like the amplitude multiplied by a general wave form, which is the complex exponential, which counts the wave number x, the wave number y, and the frequency omega. Okay? So, if we insert this expression here within our system, okay, so it's a little bit boring, but what we obtain will be system which has only W, U, F, V, and K, so it's minus 1 W minus F, V equal minus K X G, A minus E, W, V plus F, plus h I k plus u plus I ky v equal to 0. So a trivial solution for this is obviously that eta is equal to u is equal to v is equal to 0. But if we can analyze this system and construct the determinant of this system, which is composed by all the coefficient to the which multiplies capital U, capital V, and capital A, we obtain. So by obviously considering bringing this on the left hand side and putting in line U, V, and A, so a possible solution can be found by solving the equation that comes from the zero determinant. And what we obtain is actually the dispersion relation. Okay? So what we obtain is a relation which relates omega actually to k, to the wave number. Okay? The frequency to the wave number with the parameters f, g, and h. So we are not solving precisely the equation because our hypothesized solution is the one that you can see over there. So a Fourier-like solution, so wave-like behavior. But the most important thing is understand what is the meaning of the perturbation. So which is the frequency of the perturbation. So this dispersion relation has two solutions. The first one is omega equal to 0. And omega equal to 0 is a steady geostrophic flow. Okay? Why? Because if we consider omega equal to 0, our solution becomes steady, independent by t, and our system, if we neglect these two, the term related to t, simply become just a pure geostrophic flow. Okay. The other solution, which is more interesting, is this one. So, which comes from putting equal to 0 the expression between parentheses. So, this expression here tells us that omega is equal to x squared plus gh k squared, where k squared is actually the square sum of k squared plus ky squared. So it is the sum, the composition of the two wave numbers, okay, along x and along y. And since this term is always positive, it means that this is always larger than f. Okay? That's why we call superinertial traveling waves. So Poincare waves are superinertial traveling waves. If we have f equal to 0, so we are arresting our rotation, omega will be simply k gh. And since we can define the phase velocity as the ratio between omega and k, this is again nothing more than the surface gravity waves, okay? So this means that omega, our frequency, will be included between a range which starts from F and goes to KJH. That's why the Poincare waves are also called inertia gravity waves, because this is our inertial extreme case, okay, when omega is equal to F, and we reconsider again the inertial oscillation, and these are the velocity of the surface gravity waves, okay? So Poincare waves or inertial gravity waves. So actually, we can consider also two cases of high frequency or low frequency. So for high frequency, it means that we have large wave numbers. So large wave numbers means small wavelength, okay? So very small disturbances. So we can say that in our expression for omega, k square is much larger than f square over gh. But f square over gh is nothing more than 1 over r square, okay, where r is the Rossby radius of deformation. So it means that the wavelength that we are going to want to consider for the high frequency will be much smaller than r. Okay? So since, don't forget that lambda is equal to 2 pi over k, okay, is the inverse of the wave number, and of course omega is 2 pi over t. So this will be like 2 pi over lambda squared, and if we reconsider this discontinuity, we will have that when we are considering high frequency, we will considering very, very short length waves compared to the Rossby radius of deformation, which is a parameter of our solution, okay? So when this term is much larger than this one, it means that, of course, this part here will be simply equal to this one, okay? Because when this is much larger than this, it means that GHK squared will be much larger than F squared. So F squared doesn't can be neglected with respect to the second term. So we come back to the we are very close to the no rotation case. And again, we can say that the Poincare waves in case of high frequency, so we are exploring the wave number space. So when we have very, very big, very large wave number, which means short wavelength, with respect to the Rossby radius of deformation, we will have that our solution will travel with the surface gravity phase velocity. In the other case, k squared much smaller than f squared over gh, which this is equal to 1 over square, it means, of course, that we will have wavelength much larger than r. And in this case, if this term is much smaller than this, of course, we will have that u is equal to f. Okay? So this expression here was actually that we just found from the analysis of the dispersion relation, actually correspond to the two extreme cases of high frequency and low frequency. So in this case, we are again in the solution of inertial oscillation, okay? Which is very interesting because the inertial oscillation that we analyzed at the beginning as a very simple solution of the rest condition for a rotating flow is actually a special case of barotropic waves, Poincare waves. Okay, so in the most general case, our phase velocity is dependent on k and is equal to f squared plus gh k squared over k. Okay? So this is the most general expression that we can have for our phase velocity. Of course, again, if we are going to the two cases, we will find again or gh over squared in the case of high frequency, or f over k in the case of, which is omega over k, of course, and omega equal to 8, in the case of low frequency. But in the most general case, we have that C is dependent on K, which means that waves are dispersing. Yes. So in the most general case, Poincare waves are dispersive, but become non-dispersive in the two extreme cases. Okay? So, if they are dispersive, like here, actually the dispersion is a sort of decomposition of the signal and decomposition of the energy in the different phases. Okay? So the signal is distorted. Otherwise, if it is non-dispersive, like in the two cases here, the signal remains packed. And this is very interesting because Poincare waves actually can be used to explain tsunamis. Okay? So tsunami actually it can be, let's say, quite analytically, in the very first approximation, can be represented as Poincare waves, non-dispersive Poincare waves, which travel at c equal to square gh. Okay? So, why this? Because they are very fast. So you know that if you look at the tsunami wave, you have that the oscillation of the flow is not bigger, but the velocity of propagation of the signal of the disturbance, which is created by an earthquake over the bottom, is very fast. And the fact that it is non-dispersive means that the energy is maintained constant over the fluid column, which means that if we have h order, let's say 4 kilometers, like unfortunately happened some years ago in the Indian Ocean, this is traveling with a velocity which is g over h. So can you find, so we have 10 multiplied by 4 to the 10 to the 3, so we have 4,000, which is 200, so it's 1, 2, so it's 2, yes, 200 meters per second. Okay? So it's extremely fast. But the problem is that when it approaches to the coast, the energy is not dispersed because this is a not dispersive wave. So it means that the fluid column maintains, of course there will be some boundary effect, of course, but by the way, what you have is that you are looking at the waves, which is like 10 meters or something, okay? Very fast, extremely fast, extremely dangerous. Okay. Good, so we can put our dispersion relationship over a Cartesian plot which has kyr on the x and w over f on the y, and what you have is that the Kelvin wave is behaving in a constant, has a constant coefficient between the w over f and ky, because we can apply the Fourier-like solution also to the equation that describes the Kelvin wave, and what we obtain is this expression here. While the Poincare wave, of course, can, since they are dispersive, they can have different, they can assume different values according to the value of k, while the Kelvin wave is strictly related to the ky multiplied by r. And in particular, we have that when omega is equal to 0, we have geostrophy. When omega is equal to f, we have inertial oscillation. Okay, so that's why Poincare waves start to be present with omega larger than f. When we are at k very small, we are at low frequency, so wavelength much larger than the Rossby radius. When we are at very large k, it means that we are considering very small small waves, and which are actually too fast and too short to feel rotation, and so they behave like gravity waves. Okay, so the solution of Kelvin wave as omega over f equal to kyr can be found with Fourier-like solution in the equation for Kelvin wave, considering only, obviously, the wave number along the y direction, okay, because we do not have anything about the x. Okay. Okay, so looking at that plot there, we can ask to ourselves if the barotropic wave system can actually allow for solutions that stays here, okay? So, which are actually when omega is much smaller than f, okay? So, we are, Poincare and Kelvin waves are super inertial waves because omega is much larger than f, okay? So, we have frequencies that are much higher than the inertial frequency. Our question is, do the barotropic waves system allow any other kind of solution? So we are still considering, don't forget, geostrophic flows, and to the geostrophic flow we add disturbances. One disturbance given by the presence of a boundary, one disturbance given by, let's say, the general case of non-dispersive waves like Poincare waves. So, of course, the answer is yes. And what we have is two more waves. One is the Rossby waves, the other one will be the topographic waves. So, Rossby waves and topographic waves are very, very similar. The only difference is related to the fact that the disturbance that created these waves, one is related to the planetary effect, the other one is related to the topographic effect. So let's start with the Rossby or planetary waves. So the RAROTROPIC actually are based on the fact that we always have considered f like a constant, right? And moreover, we also consider the f-plane while where we didn't want to have a big extension of our meridional length, just to consider f very small, let's say very constant. And this gave us the opportunity to consider f-plane, and so the non-divergence of the geostrophic flow, blah, blah, blah. Okay, so Rossby, who was another very important scientist from Sweden, he said, okay, let's try to expand via Taylor the expression of Coriolis parameter, considering one more term, okay? So I'm considering that f is equal, okay, to f0 in this case, so the value of the Coriolis parameter at the latitude phi0, plus a sort of a term which is much smaller than this one because scale with a, and a here is the radius of the Earth, which is dependent on the cosine of the latitude. That's why I call a new parameter, which is called beta0, beta parameter, which scales like 2 omega over a cosine of phi0. And I can write f as the sum of f0 plus beta0 y. Okay, so I have a dependency of f in y, which is different from 0, and actually is exactly equal to beta0, the beta parameter. So, of course, this new approximation, which is a little bit more, let's say, realistic than the f-plane, is called beta plane. Not very much fantasy. And if we consider the value of beta 0, so if f0 has value of 10 to the minus 4 second to the minus 1 at the mid-latitude, when phi 0 is order 45 degrees, beta 0 will be 10 to the minus 11 meters minus 1 second minus 1. Okay? So we can calculate it, of course, because this will be actually f practically divided by the radius of the Earth, which is order of 10 to the 5. That's why we obtain 10 to the minus 4 divided 10 multiplied by 10 to the minus 5, and so we obtain 10 to the minus 11. Okay. So of course, if we consider our length scale of our phenomena L, we will obtain, and we give to y the scale of L, we will obtain that beta 0 L, we will call beta 0 L over f0 is much smaller than 1, okay? Because if you multiply this by something which is like even 10 to the 5 meters, you can have a number which, okay, maybe it's too much, like this. We can have that beta is much smaller than 1. And this is called planetary number. Okay, so now what we can do is to substitute to the expression of the Coriolis parameter here in our system, the expression f equal f0 plus beta 0 y. Of course, this also tells us that this term here, of course, is much smaller than f0, okay? So again, like we did with the Boussinesq approximation, is like we add a sort of perturbation to f. Okay? That's why Rossby called this like a planetary effect, okay? A planetary perturbation, because it's given by the fact that we are actually on the planet, and that f, the Coriolis parameter, has a meridional dependency, which in the most general case cannot be considered as constant. Okay, so what we have here is dtu minus f0 plus beta 0y equal that here. Here we will have dtv plus this is v f0 plus beta 0y u, and this is the same. Okay, so if we look at the equation, at the new equations here, what we can consider, we can find is that they will be composed by large terms and big terms, and small terms. Sorry. So large terms are the terms which are related to the geostrophic flow. Okay, so still thinking that we are a geostrophic flow which is dominant. On that geostrophic flow, we are adding some disturbances. The disturbances are going to create the barotropic waves. So all the small terms will be related, for example, to the variation in time with u and to the planetary effect, while the large term will be related to f0 and to the gradient of pressure. Okay? So this means that if we neglect the small terms, okay, we can do it because they are much smaller with respect to L, to the large terms. If we neglect the small terms, we just found the usual geostrophic solution, which will be, in this case, v equal to g dx eta over f, and u equal to minus g dy eta over f. And of course, the continuity equation will just remain equal to the divergence 0 for the f-plane approximation, because this is a term which is much smaller, which when we do for example, we divide everything by h, and we just remain with the divergence free. Okay, so in first approximation, we have the solution is equal to the geostrophic flow. If we take the geostrophic flow and we put the geostrophic flow within the equation again, exactly like we did for the Ekman layer, we solved the geostrophic flow, we found the geostrophic solution, and we put the geostrophic solution in the system. So what we will obtain will be something like minus g f0 dyt second eta minus f0v minus beta 0 g over f0 y dx eta equal minus g dx eta and g f0 dyx t eta plus f0u minus beta 0 g over f0 y dy eta equal minus g dy eta. So what I did, I substitute here and here the expression of the geostrophic flow and left the geostrophic term as it is. Okay? So from this, we will obtain again a solution that, for example, you can say here, v will be equal to G F0 dx eta, which again is the geostrophic solution, plus all the other two terms, okay, which actually are the perturbation. So you remember that I told you that we always can consider, in the most general case, our geophysical fluid dynamics phenomena characterized by having a velocity which is related to geostrophic flow plus a series of terms, okay? For the Ekman layer we had the wind-driven term, or the, let's say, bottom, the solid bottom related term. Here we are having something which is geostrophic flow plus something related, which we call a geostrophic, okay? So another component. So if we use V and U and we put all within the third equation, okay, the continuity equation, what we will obtain is this equation here, which actually solve the eta unknown. So variation in time of eta equal to R square, again the Rossby radius of deformation. Then we have the time derivative of the Laplacian of eta minus this term here, beta 0 R square, which depends on the x derivative of eta. Okay, so again here I can use once more the Fourier-like solution for eta, and I found the new dispersion relation. So new dispersion relationship for the planetary or Rossby waves has a behavior which is related to beta 0, R squared, and then there is a term which depends on kx, and in the denominator R squared multiplied by k squared. So all this term here can be positive. So it means that if I take the so if beta 0 is equal to 0, let's do the from the beginning. If beta 0 is equal to 0, of course omega is equal to 0. So again, I can find that this term goes to 0, and I come back to the usual geostrophic flow. Okay, there is no planetary effect. Beta 0 means that I do not consider any perturbation to the Coriolis parameter, and so I just consider geostrophic flow. So our first hypothesis was to have omega much smaller than f. This was what we asked at the beginning, no? So we wanted two more possible solutions to our linear wave dynamic system, which had omega much smaller than f, so subinertial wave. So here again we can consider the two cases. So we have that lambda again will scale as L, that will scale as 1 over kx or 1 over ky. And so we can have shorter waves where lambda is smaller or order than r. So it means that r squared, k squared is larger than 1. And if r squared, k squared is larger than 1, means that I can neglect this one, and what I can do is to simplify this equation. I lose the dependency on r squared, and what I have is that omega is like beta 0 L. Okay? because what we obtain is that r squared and r squared can be neglected. I just have an expression which is k over k squared, which means 1 over k, and 1 over k scale like L. Okay, so omega scale like beta 0L. But beta 0L is much smaller than F0. Okay, so we are happy. We are exactly what we wanted to look for, sub-inertial wave. Let's look also to long wave. So similar consideration, R squared, K squared, smaller order than 1. In the extreme case, we can neglect the second part, so we will have that omega will scale like beta 0, R squared L. Which is also L. And since R over L is order lower than 1 because of this case here, this is again ordered by beta 0 L, and again is much smaller than F0. Okay? So Poincare waves in the two extreme are much smaller than F0, and so they are called subinertial wave. Let's look a little bit more about the dispersion relation. So if we look for the phase velocity in the x component, this will be omega over kx, and omega over kx is minus beta 0 r squared over this. Okay, and all these terms are by definition positive. Okay, if I neglect this, which can be in general positive or negative, what will I obtain if I want to calculate the phase velocity along x is only this case, this expression here. But this expression here is positive, so it means that the phase velocity along the x will be always negative. Okay, that's why we call about the westward propagation. So in the northern hemisphere, if we have the north here, the south here, Poincare waves will always propagate with the north on its right. Okay, always against westward. While the propagation along y, I mean on the meridional distance, can be positive or negative because we cannot find any hint about the propagation along the y. Okay? Most important thing is if we consider the group velocity, which is the derivative of the frequency with respect to k. Of course, we are, I didn't say, but it's clear that we are dispersive waves. So if we put omega over kx plot, what we will have will be something like this. Okay? So we will have that when kx is equal to 0, of course omega is equal to 0. Then we will have very small value of omega for larger k, because when this is much, much larger, of course this goes to 0. And then we will have an increasing in this direction up to a certain value of kx, then a decrease, and then again an increase. Since the group velocity, which actually is the velocity of the energy, so the velocity of the information, we will have here a positive derivative. Okay, so positive derivative means that the group velocity is positive, so it's eastward. Here we have a negative derivative, so westward propagation of energy, and here again eastward. Okay, so it means that when we are close to k, close to 0, so for k very small, K very small means large wavelength. So largest wavelength will travel westward. Shorter wavelength will travel eastward. Okay? In our planet, the largest wavelength can be, this is a model, let's say, very simple for the propagation, for the westward propagation of the subtropical jet, which travels westward, while the polar jet, which actually separate the polar mass from the maritime, let's say, mid-latitude air mass, will travel eastward, okay? And so this gives us a very simple, let's say, first approximation model to explain the general circulation in our atmosphere, in this case. Okay, so we can even rewrite this equation here by using can you allow me 10 minutes more to finish? You have other lesson? Okay, so we can conclude. So, if we rewrite the dispersion relationship, is Kx plus beta 0 over 2 omega square plus Qy equal to beta 0 square for okay, so this is just a rewriting of the dispersion relationship, keeping in consideration the fact that we are plotting the dispersion relationship on a chart which have kxr and kyr as a dimensional axis. Okay, so this is actually can you recognize? Well, it's easy. If we are in a kx or ky, it's exactly it's the path of a circle which is practically based, which has a center which is 0 in y and minus beta 0 to omega in x, and this is the radius, right? So this radius, let's call it r lowercase, of course can be positive or at minimum 0. It's not possible that the radius, being a distance, can be negative. So here, this actually gives us a limit for the frequency. So the frequency that we can have in Poincare waves is actually limited by this value, so it's strongly related to the planetary effect. And when it will be equal to 0, what happens is that our system will be practically concentric, will be located on the point -1, okay? Because we just put this term here, and we will obtain, if you simply substitute omega here, you will obtain -1. So all this circle here, which has practically each of this circle correspond a fixed frequency. So we will have that omega will goes maximum to beta 0 r squared and minimum to omega equal to 0. And the increasing of the circle means a decreasing of the omega, because the radius is inversely proportional to the frequency. So we know that the extreme case is when beta 0 is equal to 0 and we have omega equal to 0. So this radius will goes like this, and then like this, and then like this, and then finally they will completely parallel to the y-axis. So the group velocity is a vector which is perpendicular to the point kx, ky, and is always directed versus the center. Because if we consider the derivative of omega with respect to k, and thanks to the construction of the geometric construction of the dispersion relationship, we will have that the group velocity always will point toward the center. The direction of propagation, you can see that kx are allowed only to be negative, so that's why we have that cx is always negative. Okay.
So that's the plot of a surface.
That's no, it's not a plot of the surface. You mean the surface of the wave?
Of the no, mathematically. That's omega.
Yes, exactly.
The gradient of omega is.
Yeah, exactly, perfect. Yeah. Okay. Last few minutes to consider only, very fast, so I don't want to give to go too much in detail because the analysis is very similar to the planetary effect, and is the topographic wave. So topographic wave is another solution of our system, but now we are no longer considering a perturbation over the Coriolis parameter, but over the dH. Okay, so up to now we have always considered the bottom as flat. Now we allow to have a inclination of the bottom, and the inclination is described by another term which is alpha 0, and again we can exactly like we did in for the planetary effect. We have alpha as a topographic parameter, which is not beta 0 L over F0, but alpha 0 L over H0. So before we had F equal to F0 plus beta 0 Y. So we just change H0 instead of F0 and alpha 0 instead of beta 0, and we will obtain again this term, which again tell us that this perturbation here is much smaller than H0. Okay, exactly. So mathematically is exactly the same. What we do again is to consider large and small terms. Of course, now we leave F as it is and we change this part here. Okay, so we will change H here, putting H0 plus alpha 0 Y. And what we will obtain will be again a solution which will have geostrophic leading term plus a geostrophic perturbation term. Again, we will solve the system, and we will put the two equations U and V, the two solutions U and V in the third equation, and again, as you can see, we will found the equation of continuity with the perturbation. Okay? So that you can see that is very, very similar. So you can see the first two terms are exactly the same. The only change is the third term, which here depends on beta 0, and here depends on alpha 0. Okay? So there is a strong analogy between the planetary and topographic effect, and also the dispersion relationship is very similar. So again, we can find expression kx over 1 plus s r squared k squared, but here we do not have minus beta 0 over f, but we have alpha 0 g over f. Okay, so again we can find that the topographic wave are subinertial. So again, with the frequency much smaller than f. And there is a very nice analogy, because what we will find will be that the phase speed Cx, so Cx is nothing more than this expression here divided by Kx. Okay? So this, since this term is positive, the only possibility is that say Cx will have the same sign as alpha 0. So when alpha 0 is positive, Cx will be positive and will go eastward. When alpha 0 is negative, Cx will be negative and so will go westward. Okay? So basically, the topographic wave will propagate in the northern hemisphere, consider F positive, with the shallower side on their right. Okay? Shallower side on their right. Okay? So if this is shallow, I'm going in this direction. That's why we have this analogy with the Rossby wave, shallow north and deep south. Okay? So Rossby waves are moving in the northern hemisphere with north on their right side. Topographic waves are moving with the shallow side on their right side and deep and south on their left.
Professor, so if we have a superposition of a planetary wave with a strong topography, if we have the sum of two different Rossby waves?
Exactly.
Because the problem is linear, and so
of course. Well, we are still trying to keep everything as linear as possible. Since they are, related to topography and rotation doesn't have anything in common. I can consider something which is flat with a planetary effect and the other one, and also both of them. That's why when we consider both of them, so we can, this is the last part, where we found the potential vorticity. You remember that potential vorticity was the sum of ambient rotation, ambient vorticity, relative vorticity, and H. Okay, you remember we found it from the barotropic flow. Don't forget that these are barotropic flows, so we are always still in that case. So if we substitute to F the perturbation of the planetary effect, and to H the perturbation due to the topographic effect, we can solve Q, make an approximation here to find this expression, which is based on the fact that I'm writing the expression of the potential vorticity, which is Q equal, there is a big expression in the numerator and a smaller, shortest expression here. So I can A and B, so we'll have A and B to the -1. Okay? So numerator, which depends on F and all the vorticity part. Denominator, which is related to the H0. Don't forget that we also have eta, because this is H. So H is capital H plus eta. Okay? And this actually will be like 1 plus epsilon something. Okay? And this epsilon something, which actually is nothing more than this term here, because we know that this and this are much smaller than this. So we can rewrite this and put everything like on the same line on the numerator, and we found an expression of potential vorticity which is depends on F0, beta 0, alpha 0, F0, H0, and then the relative vorticity, and finally a term which depends on eta. Okay? So it's again a simplification. Okay? Don't lose in the calculation, but just keep the concept. So what we will have is that our potential vorticity Q is as a leading term, which is F0 over H0, okay? The first term, F0 over H0, okay? So a simple fluid column with, which is traveling at F0, with F0 Coriolis parameter over an H0 depth. Then we have two terms which depends on Y. So we have a gradient of the potential vorticity which is equal to beta 0 minus alpha 0 over H0. Okay? So the gradient of potential vorticity is the effect that actually gives the bouncing effect to the propagation of waves in our planet. Okay? So now it's a little bit too late, but if you consider from a state of rest, which is characterized by higher values of potential vorticity going in this direction. So it means that I'm going towards north, because this is positive, beta 0 is positive, so I'm going toward north, and so I'm moving over, I'm considering a perturbation over my Coriolis parameter, or also I'm moving toward a shallow configuration, okay? So from this we can keep a parcel over this, this system and try to point out that every parcel will be subjected to a vorticity, to a potential vorticity, which actually will move this parcel, will give to this parcel clockwise vorticity in this side here, anti-clockwise vorticity in this side, and therefore this parcel which is here will go towards zero, yes, toward the southern position, because it's like it is between two gears, like in this configuration like this. On the right side I will have the opposite, and so it means that if I apply the same effect on all the parcel, the total effect is to move the entire fluid flow towards west in this case. So a similar explanation can be found also for the topographic wave, where we have not just a change of vorticity, so with greater f and smaller f, but a change in the dimension of the fluid column. So since this is a shallower side, I'm going to squeeze. So if I squeeze, of course I create some vorticity which is clockwise. If I go in this direction and I have I go towards a dip, so if I increase h, I have to increase also the vorticity, the relative vorticity, so I have anti-clockwise vorticity, and so again a parcel which will be here will be moved towards this direction, and a parcel will be here will be moved towards the opposite direction. Okay? Good. Okay, so it was quite fast. I can understand, because it was not easy to cover all this barotropic waves in just one lesson, but unfortunately we had to cope with that this year. And have a look to the chapter related to the barotropic waves. At the exam, if I will ask you something related to the waves, of course I know what I did, so I won't ask you exactly the derivation of the topographic waves. But if it's important that you have an idea of the, let's say, of the concepts that bear us to the definition and to the analysis of the different cases of the four